Alright, good morning, guys. So I thought this giving you a video lesson on linear structures. Here's what I'm going to do today. The promise. So I'm going to go over oops, list data structure conceptually and introduce the list ADT. Then I'm going to go over array based and link based list implementations. Then I'm going to go over stacks, both ADT and the implementation, and queues, both ADT and the implementation. So that's the plan. So let's go through this. So let's talk about what is a list. Okay. So its definition is basically it's a finite ordered sequence of finite and ordered sequence of data items or elements. Okay. So what ordered means not sorted. It's really important that you understand that. It means there's an index for each element position. So for example, if we take an array, we have an index starting from 0 to the end of the array. So it's kind of same idea going over here. So each element can be identified by a position. We call it index. That's what ordered means. Element may or may not have a single type. Okay, it's not a requirement. Okay, so let's talk about the ways we can implement a list. One is we can simply use an array, simple array. So we call it array based list or simply array list. We can use pointer to link all elements, and we call it linked list. Okay, so we can use we call it link based list or linked list or pointer based list. So it's good to support any kind of implementation for both concepts. So that means we'll have to sort of write a list ADT so that we can support both. Okay. All right, let's talk about the features of a list. All right, so when there's no element in a list, we say it's empty. And total number of element is the length of the list. The beginning of the list is called head. The end of the list called tail. So we can now propose a notation for list. It's just going along with math. So if the list has n items, n items of A, then we can denote the first item as with 0 and then the last one with n minus 1. So we can simply, like following mathematical sequence, we can write our array like this. Okay, so empty list is like this and non-empty list is like this. Okay, continuing with features of a list. Okay, so let's talk about basic operation that can go to list abstract data type. We should be able to create and clear. We should be able to grow and shrink. So for example, append or remove. Okay. Right, we should be able to insert and remove as well. We should be able to access or change an element value. We should be able to access next or previous values from the current value. Okay, so for a list, most of these actions usually happen at the current position. You will see that there's an exception for an appending. So appending always happen at the end, but most of the other operations should happen at current position. So our ADT should be designed based on this idea of the current position. Okay. All right. So this is just a ADT that we have in our code base. You can simply go over it. So it's a abstract base class named list, and then there are two private variables. One is equal operator, and then it's to basically protect assignment, and then basically list, and then copying. So it's to protect copy constructor. Okay. So basically they are private. That means outsiders can use the simple assignment or copy constructor, simply to avoid complications. Okay. All right. And then all of these are the operations, and then they are all virtual, pure virtual functions. That's why we have equal 0 over here. And you can see also that there's a virtual destruct. Okay. So that means basically you can create a subclass out of this list ADT safely. So that's why we have the virtual destructor there. Okay. All right. So without this, we may look for like memory leaks. Okay. All right. So, and this is what we are provided from the book. Okay. And continuing with the ADT, and then we have rest of the functions. Okay. So move to start and move to end, and the previous, next, length. A list has a length and the current position, and move to position. So you should be able to move to a position, and then whether to know it at the end or not. Okay. All right. And then get value. Okay. And get value basically return the value at the current position. So basically item type, list item type. Okay. All right. All right. So list. So one way to implement the list ADT is to use a simple array. Okay. So we have an array. So array in this example, array has 10 elements. So the length is 10. Then they are indexed with 0 to 9. And you can see that the array is the size is fixed, right? And we have up to element 5. We have elements. Okay, 3, 5, 1, 2, 9, 7. So these are data. This is the index. Okay. All right. So it's the size is fixed. So that's the internal storage. So basically the entire array inside, size, the maximum size, which is in this example, the maximum size is 10, and the size is 5. To 5 we have elements. Current value, they're all private variables. Okay. So array positions inside basically correspond to list position outside. So basically, if I want to access fifth position, basically inside the array also is the fifth index. Okay. All right. So they're both one-to-one corresponding. And size is always less than or equal to maximum size. All right. So we call the first element is the head, and the last element as the tail. Okay. So element position I, for example, all right, for example, element position 3 is in list is stored at array cell I. So basically the same array cell, same index is going to store the same value. Okay. All right. Head node is always at position 0, and that access is basically theta 1 in time, access to the first element. Okay, because it is simply, we know that array access is order 1, right? So if you know the index, then you can directly access the array. So it's order 1 operation. Okay, that's why. So tail node is at the basically at the last non-empty node, in this case 7. So is the element, so fifth index. Okay. All right. So this is very important. So array-based list basically designed to have store continuous cells. So that means we cannot have empty values in between cells. Okay, and then or anywhere in the array of unless it is after the last, after the tail. Okay, so after tail, it's only there can be empty slots only after the tail. Okay, so and the other one is basically insert, remove, and append. All three operation must honor this concept. Array-based list can't have vacant cells, and for obvious reasons, right? So it could prevent complications having empty in between, and also it could save memory as well. All right. All right, so append always happen at the tail. So that also take order 1 time, because we can directly access this last element and then put our data item in there. Okay. All right, insert and remove at tail also takes order 1 time. So big theta of 1. Okay. So inserting at the tail or removing the last element, they both have big theta of 1 time. So inserting and removing anywhere else, we need to basically shift elements. Okay, so insert requires shifting towards right. For example, if I have to insert at the index 3, then basically I need to make the index 3 empty. That means I have to move 297 all the way to the right, and then create an empty space so that I can put the new value at the index 3. So so that means it requires shifting elements, and removing requires shifting element to left, because we cannot, once we remove an element, we cannot leave that space empty. So we have to shift the all the element to the left of the removed slot, towards to the right of the removed slot, to the left. For example, if I am to remove this value 1 from index 2, so then this is going to become empty. So I have to now move all this to that way, so to the left. So that means on average, in the worst case, okay, which is average is anywhere in the list except the tail. The worst case is basically when the insert, when you want to insert at the index 0 or when you want to remove at index 0 at the head basically, then you'll have to shift element um, all the n elements basically towards either left or towards either right. So that's has big theta of n time. Okay, both average and worst case. All right, so let's take an example animation of um, insert. Okay, so we need to insert at number element 6, new value 6 at head right here at index 0. So let's play this one. Okay, so we need to basically move elements. In this case I moved 7 to right. Okay, so that's the links go back. So the length of the list is 5. Sorry, length n is number of items in the list is we have 6. Okay, so this is the one shift, second, third, fourth, fifth, and sixth. So it's order n operation. Okay, so I shifted all the elements to the right and then put 6 in there. Okay, so now the length is increased to 7. Okay, so again need to have empty slot at the end, at the head, and you cannot override the head. So that means this is the worst case, and then we have to shift all the element to right. Okay, so this is the order n time process. All right, so before we go into linked list, let's play some of these animations in the book. Okay, all right, so insert, and then unfortunately this seemingly Java code here in this code base, but you can simply take it as a um, pseudocode. It's really really close to our C++ code, but and also you can, they are readable, so you can take it as a pseudocode. Okay, so inserting. Okay, so we are going to insert at the beginning. Okay, at the head. Okay, so we are basically moving all the element, and you can see that it's a for loop. Okay, so we make room. Okay, and then we put the new element at the head. Okay, so and then after that we have to increment the list size. Okay, all right, so and that's it. So that's the insert operation. Append and remove. So take a quick look on append. So we are appending. Okay, so simply we put it there because we have an empty slot at the tail, so we put it there, and we have to make sure we are not going above. Remember, array list has a fixed size, so we have to check whether we are going above or not, and if we are not, then we can put the new element as using the array assignment feature, and then we have to basically write here. Let me annotate. So right here you can see that we are incrementing the position as this size as well. Okay, so everything in a single line. Okay, so we are assigning that value to that. Okay, so and then this is the assignment of that value, and this is the incremented size, right? This one. Okay, All right, and then it's a Boolean function, so we return true. Okay. All right. Okay. So let's continue. Okay. And next, this one, basically, okay. So this is insert. Let's see. Oh, do this remove. Okay, removing this element. Okay. So first we need to basically take it out. Okay, and then we have to shift the element towards left. Okay, and that's actually a for loop over here. Okay. Okay. All right. So so let's go back to our code base and check on this. Okay, so this is the I actually posted this code already in Canvas. Okay, so this is the all the header files that we have. I'm going to show you the implementation of the array list. Okay, first let me go over this. Okay, so okay, so we are actually inheriting from the list ADT. Okay, and it's a template. Okay, and there's a maximum size, so it's the maximum capacity inside the list, and list size, the actual size, the current position, and then the array inside. They're all private variable. That's what we discussed, right? And then the constructor and takes a default size, and in this case 20. And if we don't pass any size to our constructor, then the maximum size will be 20 of the list. And then list size and current position, they're all gonna get 0, because we gonna basically create the array list empty. So and then it's going to be a dynamic array, basically of that maximum size. Okay, so since this is a dynamic array inside, we have to delete it. Okay, so in the destructor, so that's the delete operation inside. Okay, and clear basically reinitialize an existing list to empty. Okay, so here also we have to delete it first, and then recreate the array. Okay, and reset the list size. Okay, and insert operation, we can see the for loop. Okay, but we have an assertion to make whether we reach the maximum or not. Okay, so we have to check for that. That's actually assert. This assert function coming from utilities. Okay, you can see assert over here. Okay, so it's a utility function. All right, and then append just, you can see that just single line of code after assertion, so it's order 1, and we can see over here in insert, it's could be up to big theta of n. Okay, or order 1, order n, sorry. Okay, and the remove, again we have to make an assertion whether the list is empty or not. Okay, and then basically we are returning the removed element, so that's the element. And then and removal happen, it's very important that you have to understand removal happen at the current. Remember we talk about that most of the operation happen except append happen at the current position, so we're removing the current element, and then after that we have to shift element. And so this could be worst to average case, big theta of n operation. And at the end we have to decrement. It's really important that we have to decrement the size because we are removing element. Okay, and then move to start, you move the position to current position to start, and to end you move it to the end. And there's a previous and next method to increment or decrement the current position, and this these are useful whenever you want to iterate the list. Okay, and a length, and it returns the size, this size, and current return the current position. Okay, current position return the current position, the index value, and move to position basically take an index and then move to move the current to that position. Okay, so in here it again you have to make an assertion to check whether, to make sure we are not going above the list size. Okay, list size, in this case list size. Okay, not the maximum size, list size. Okay, and then the get value basically returns the value at current position, so it's actually return the data. Okay, and then there's two more functions. Is at end, and then basically it actually returns whether we reach the current position at the end or not. Okay, so it's a boolean returning function, and this one simply sequential search. I added this function, and also binary search. I also added this function. They are not coming from ADT, because remember this is a subclass. You can add your own functions as well. Okay, so and then recursive binary search. So I have added all those three methods in there. Okay, so that's additional stuff. Okay, so let's check our array list and then test it out. So we go over this. This is the driver program. So I'm actually annotating where I'm starting and then ending. Okay, so we are going to start testing on array list. So what we do is basically we're gonna basically call the constructor, and then here I'm going to create just integer array list. So pass the type, and then array list, and then this, in this case I'm creating a list maximum with maximum size 10. Okay, so then basically I'm up to 10. I'm going to append the same value I. Okay, and then so let's check that, and then basically what I'm going to do is I'm going to check the current position. Okay, and this will be 0. Okay, and if you take append again, and let's go to a list, append, and notice we are not changing the current positions, though we are appending. So the current position, it's, if it is the brand new created list, it's at 0. Okay, and we're going to verify that as well in the mean. So let's run this one and see what we're going to print up to this line 22. Okay, so I'm going to scroll all the way to the top. So we are testing on list. Current position is 0. Okay, and has data 0, right? Because I'm adding the ith value. Okay, so and then I'm going to use the move to position function. I'm going to change the position to 5, the index. Okay, so and then I'm going to print that, and that's what we have over here. Okay, so current position after is 5 now, and it has data 5. Then I'm going to remove that current position, current value. So that basically says after remove, now 5, position 5 has data 6. And you can see that after remove, I have shifted all the data to the left. So position 5 has data 6. Okay, then I'm going to insert. Okay, I'm going to insert number 5 again to current position. Okay, so current position is 5. I'm inserting 5 as well. So I basically recovered the original created list. So insert. So after insert 5, position 5 has data 5. Okay, and then basically at the end, so right here, so in 30, I'm basically making the current position move to start. So I am going to basically print entire um, array list. And here's how I do it, right? So basically I have to, I'm using for loop, and then I'm going to do it all the way up to the length of the list. And basically I need to increment the I value, and then basically I get the value. Okay, so basically I think I don't need that. Actually, I'm not returning that. Okay, so I basically put it here. Okay, and basically I get position 0 has data 0, likewise, right? The position, and this is the current position, which I'm starting from 0 because I moved the current to 0. Okay, and then basically go all the way to the end. Okay, and then that moving of position to the next happen with this next. Remember I said, okay, so next and previous is used as two functions to move the position. Let's just first let me comment out this and then run. Okay, so I'll get an assertion error. See, okay, see that position 10 has, so its assertion failed. The reason is this: I didn't move the current position because right here the current position was at 5, so I'm going to start at 5 this for loop. Okay, so if I want to, and print the entire list out or access the entire list, then I first make sure to move the current position to start, and then do the accessing. Okay, so let me do that again. So so we don't have any assertion error. Okay, so okay, so we are here. So I'm going to now do this. So I'm going to remove this next, and let's see what we get now. Okay, all right, see now basically I have all the zeros because when the for loop iterates, but the position is still now moving because I'm not using next, so the position will be at the same position. So basically I am printing same value. So you have to use depending on the way to the direction of your iteration, you have to either use next or um, previous methods. There's also another method that you can use. You can use go to position as well. Okay, all right, so that's it. So that's array list. So let's go back to our lesson. Okay, all right, so we're over here. Gonna start our linked list lesson. Okay, all right, so the link using pointers are the other way, the next way of using and implementing list ADT. Okay, so in this case we're going to use pointers to connect each object. We call them nodes. All right, something like this. So this is a non-empty list. So we have the head node, we have the tail node, and we have the current. The similarity to with the array based list. Okay, which basically represent this pointer. Okay, and this is empty list. So everything, the current, the head, the tail, all empty at the first node. Okay, all right, so basically the linked list allocate memory dynamically, and you know that whenever you use pointers, and then it's actually dynamic. Okay, So and then so that means there's no limit to the length, there's no maximum. Okay, so as needed, as much as all the way up to the memory available in the system, literally you have the size. Okay, so basically each node, data item in each node is linked by a pointer. Okay, so that's that pointer. We use the arrays and then these boxes as symbols. Okay, so this grayed out part and this array basically comprise the consist with we call it basically um, uh, comprises the pointer. Okay, all right. So basically the node behind, for example, if I am considering this guy and this node stores the address of a given node. So basically if this is my current node or the given node, this guy stores the address to that, and that is this pointer. So it's really important that you understand that this is my current node, the guy behind stores the address to that, which is the pointer. Okay, all right. So like right here, having this empty head node right here is basically solve many problems, and you can see it in the online book. Okay, all right. So this is the list ADT. Okay, so now with an array list we have an array, so we know that arrays are given from the system or the programming language as a storage container. So and we know how to access or work with an array. Unlike that, for a linked list, this node we have to actually explicitly create it. Okay, and that is where many students are struggling with, because to understand this new thing that is very different compared to the array. Okay, so that's the class is basically linked node class. All right, and basically it's a class. Okay, and for example in this throughout this class basically we use the object oriented way of representing things, and then you may have seen in other places that people use structs and then structures and then like plain code in implementing linked list, which is not reliable, and that's why this book has taken the real approach that is reliable, because that's the one we use basically in software industry in the outside of the world, that concept, right? So that's why the author called the practical application to data structures and algorithms. So in C++. Okay, so link node, there's two public things. One is element and the pointer to the next, which is link node. Okay, and node is the same name. Okay, and then basically the constructor. Okay, so so we basically pass the element that we want to store in that particular node, and then at the initial the default value is null for the pointer when we are creating, and then there are two constructors, and then the other one is basically we simply create just a single pointer. Okay, and then at the element inside, so we pass elements and we assign it to the value that we pass value, sorry, element, we assign that element to the value we pass, and then the next is going to be next value point. So it's simple assignment to the data inside. Okay, and same thing here happen with the the other constructor as well. Okay, so basically this one create empty empty node. Like for example, creating the head node, we need to create empty one, right? So that's we use this constructor for that. Okay, all right. So now this is one way of writing linked node. Okay, and you can see that. Okay, so now basically this way of writing it, um, writing the constructor has some basically um, has has a um, has a has a drawback. So the reason is basically this new and delete the operations, they are inefficient. Okay, so basically if we can overload them with the efficient operation, and that going to be basically save space and also fast as well. Okay, so that's what the author decided to overload new and delete. Okay, so new and delete, original new and delete operators in C++, they are author claims they are inefficient. So basically in this node implementation, um, author basically decided to um, um, overload them. Okay, so in here basically we have the link, a link node. Let me just check on this. So that's the link node. Okay, so in here we have the element and the link. Okay, and then basically in the link constructor we create the link node. Okay, so these are the overloaded new operator. Okay, so basically if for this basically what the author decided was to create the thing called free list, and then whenever we delete a node basically okay, so we basically return let's talk about the delete operation right here, overloaded delete operator. So when we delete, okay, we put that item in the free list. Okay, so that's what this operation does. Okay, and then basically we basically assign it to free list. Okay, so we are putting it there. All right, and for this we need actually casting, because it need to be same type. Okay, and here it's a void pointer, that's why we need to cast. Okay, so otherwise we cannot work with void pointers. So whenever we use void pointers, we need to cast, because we don't know, we basically need to cast it to this type of free list. That's what we are doing over here. Okay, so it coming as a void, and then it become the type in free list. Okay, so then basically what happened is that as we delete nodes, the free list take those memory spaces. Okay, not the free store. Okay, because we are basically overloading the delete operator. So it's a more efficient place. And then when we create, okay, in the new operator, so basically this is the overloading of new operator. If the free list is not empty, we basically take that space from free list. Okay, so that's what happened. So then we return that temporary temp value. That's the link. Okay, so operator new returns that. Okay, so basically operator new doesn't create new value in the memory, it actually first checks the free list, and if there's a one there, then it takes that. Okay, so simply basically free list is a location that we specify for storing this deleted nodes. Okay, nodes basically addresses, pointers, right? And then if it is null, then basically sorry, if it is, if the field is also nil at the very beginning, it is also nothing there. So then basically we return new. So this is the original new operator. So we return new link. Okay. So there's nothing we can do, but we have to create a new link, right? So that's the original new operator. This is not the overloaded one. Here we are overloading, but if the field is also empty, we return. Okay. So we use that, and then basically use that overloaded operators in creation. Okay, so and that's what the link class does. Okay, so and that's it. So this is basically the two, um, um, the element and the link, and then the link class basically create them. Okay, so in here it is the same without using, that's why I use link node to avoid confusion. Okay, so and here this one doesn't use free list, and this is rather inefficient, and that's why we have this class, the link class, and this is the one that we use in the code base throughout. Okay, so it's really important to understand that concept. Try to read the book. There's a section in the book, both PDF one and then the online one has the explanation on that. Okay. All right. So let's take a look at insert. So insert operation at current, which is right here. Take theta, big theta of 1 time, and then let's see why. Okay. All right, so let's say we are creating we need to first create the node, which will have name IT with data in item 6, data item 6. So that is this one. Okay, so that's the first step. So we have to first create the data item, and then before the consistency of the list governed by these pointers. So if you lose one, basically then you lose a part of the list. So make sure you don't do that. So that means when you insert, you first have to make that link to the next one that you are the place you are inserting. Okay, not the one before, but should be the one after. Okay, that means like you have to point this to this node. Okay, so that's the step 2. So before breaking, it's really important, before breaking this, the link 9 and 7, you have to make a pointer from 6 to 7 like this. Okay, and then you assign the current next. This is the current and current next pointer, which is this, to this item, data item. Now you can basically, when you do that, we automatically break the 9 to 7. Okay, so these all 3 steps combined take big theta of 1 time, because there's no looping or anything. There's 3 operation, and the entire 3 operation is packed in this single line. Okay, so basically this right here, IT is the data item. Okay, so that's the data item creation, step 1, and this is the old current next. Okay, and we pass that to link. That's the old one. We pass that to link. Okay, and then return the next current next, right? So and then we are creating that new basically entire new node and linking it. Okay, and then see the first step, it's creating the data element, and this is the second step. You assign it, you take that old current next, and inside this constructor we create the new one, and then assigning the new node to current next. Okay, and then if you go inside the constructor, this is what we have. This is the element. Okay, and then we get a link, that's that. It's the next value is this one, and then we basically element value, we assign the element value, and the next going to be next value, which is this one. Okay. All right, so that's really important that you understand this single line actually covers all three operations. Okay, so in our code, we go to main program. So right here we start testing linked list. Okay, so in here I'm basically creating empty linked list, and then I'm appending all the way up to 20. Okay, so and then basically I'm going to print the current position. Okay, and let's run this up to that. Okay, so all right, so testing yeah, using linked list. Okay, so first before insert. Okay, right, current position 0 has data 0. Okay, so that's this line. All right, so yeah, and then because it's again appending doesn't move the current position, that's why. Okay, so then I move to position 5. Okay, and then again I'm printing it, so that's what we have. My current position 5 has data 5, and then I remove. Okay, and then I remove after remove, so we have position 5 has data 6, so position 5 has data 6. Then insert, after insert at the same position, basically right here this operation, and then basically I have data item 5, and it has data 5. Okay, and then I actually iterate entire list. Before that I move the current position to start, otherwise it will be at the 5th position, right? And then start iterating. Again I use the next on iteration. Okay, so yeah, so so that's it, and then we don't need this actually. Okay, so yeah, and then that's the rest of the printing. Okay, of values. Okay, all right, so let's go back to our lesson. Okay, all right, all right, so so let's talk about this element design. Then we'll talk about a little bit on this. Okay, so let's talk about the design choices for the list data element. Okay, okay, so we can store separate copies um, for in each data element. Okay, so basically it's, if we have a small amount of data, less duplicated, we can use actually separate copies. We don't have to deal with that. Okay, so so that's one choice. So we are just going over design choices. We can also store references. If these elements are really big, sometimes it could be our user defined object as well, the data element. So it could be really big. For example, if you take a book as data structure, and one page of text is going to be a lot of, let's say one page is an object. So a book is comprises of like a lot of pages, a lot of page objects in there. So when you do that as a list, then basically the elements going to have a lot of space in it. So instead of that, you can use actually pointers and then store references. Okay, so it's good for large and highly duplicated data. Okay, so that's good for that. And you can else you can also you can use, um, you know if not, basically the pointers increases memory, or right. So for example, if the data is really small, then pointer size and the data size is kind of comparable, and that means basically you increase memory overhead. Okay, so basically if if the data is more like really close to size of pointers, then basically the wastage ratio is higher. Okay, so there's the other risk is basically um, using references increase memory leaks. So basically when you delete, you have to make sure you delete data explicitly or manually, because C++ don't have garbage collection, so you have to take care of that as well. So use of references has those memory leaks risk. So basically, so this means basically you are responsible for manually deleting data. Okay. So let's talk about list homogeneity. So basically, if we call it homogeneous container if all elements are in same type. Okay. So we can make the type of the list fixed. So when we know that, it's less versatile. Okay. So if the type is fixed, basically it's homogeneous. Okay. And then but it's less versatile. Okay. So there are workarounds to make little bit this thing is make this process a little bit more sophisticated. So one is using templates. Okay. So and then basically you can let the compiler to choose at the time of usage the type. So it's a bit more versatile in regards to writing type independent code, but still basically it is at the end, at the time of usage, it's a single type. Okay, so um, the other option is basically we can use an ADT, and we can use the inheritance, and then we can use subtype polymorphism, and then that way we can allow several types of a single to super type to have the container. I think we did an example in the previous lesson on triangle ADT, right? So we created two types of triangle and then created one array of one vector of both types of triangles. Okay, so that's been a little bit more versatile, but still you have to have that both type depending on single super. So that means you need to practice inheritance and need to have a super class for the all those subtypes that you want to put in that single container. Okay, so you need to have a superclass of all of those subtypes. Okay, so the most like flexible way is basically if you use void pointers, then you can have any type uh, in your container, because the type is we use void pointers. So basically, it's allow full heterogeneity, is the opposite of homogeneity, right? but the problem is it's really complicated. Now you have to deal with void pointers. So the void pointers don't have a type, so it'll be like segmentation fault kind of error when you try to dereference a void pointer because it doesn't have a type. Now the compiler is confused to as to what type of value return. So you cannot dereference a void pointer. So before that, then you have to basically use typecasting to cast to the actual type, and that's also create a problem because now you need to have pre-known the type of the item inside the container to dereference. So that means you need to have that knowledge of knowing what type of uh, element that particular element is to before you dereference. It kind of um, like not a good thing because yes, you can support multiple types in a single container, but you need to have now knowledge of which type of item would that be before you do the dereference. Okay, that's this homogeneity. So let's talk about doubly linked list. Okay, so it's really similar to single linked list. Instead of only forward progress of pointers, we now have pointers allowing backward access. So there's an extra pointer now. Okay, so there's an extra pointer pointing backward access. So it's basically it makes some operations even simpler. Okay, so basically it's going to simplify all implementation of the single linked list. Okay. Okay, and again we still use empty head node. Okay, and that also solve many problems. So let's go and check some doubly linked list operations. Okay, so we're gonna go to um, right here. Okay, so insertion. Okay, all right. So we do first. In this case, we do take yeah. So let's continue. Okay, we create our node inside in there, right? 15, and then we combine it first. See that we first combine it with uh, the node to the right of the new node that we increase before we break the pointer. Okay. Otherwise, once we break that pointer, we lost the contact to that rest of the right hand side of that. So we have to prevent that. Then we basically we use a backward pointer to create point to the element to the left. Okay. All right, and then we reassign the current. Okay, then we create to complete the rest of the node pointers creation. Okay, and then the new node inserted become the current. Okay, all right, so that's the insert and append. Okay, so we go to the end, right, and we do the same. Okay, so it's simple. So you can see that the operation got simpler because of this backward pointing pointer. Okay. Okay. All right. So let's go back to our lesson. All right. All right. So let's do the comparison between list, array list, and linked list. Okay, this is the time comparison. All right. So insert, remove only at current node. Okay, you need to remember that at current node. Okay, and then take order 1, big theta of 1 for all cases. Okay, so we saw that. Okay, there was no for loop involved. Okay, and right here it's insert, remove, require shifting other element either up or down or right or left. It's a big theta of n operation for average and worst cases. Basically, yeah. Okay. And access require march down to list unless it's the current position. You need to go to that position. So you need to basically move your current position to that whatever that position to access. So that means worst case, it's big theta of n. For example, imagine you are current at the beginning of the list. If you want to access the last element, then you have to march down the list. So average and worst case, it's big theta of n. Access, it's similar to an array, so it's fast. It's big theta of 1 for any case, so it's fast. So that's why if you need fast access, you should always go for arrays unless there's um, there's no size limitation. Okay, so if there's a size limitation and then this arrays has a limited size and you know that size, then basically you can use an array because it's really array access is really fast because it's optimized from the compile itself and because the memory arrangement is sequential. Okay. All right. All right. Space comparison. Okay. So many containers, because it's a class and then there's other things inside, it needs some extra space to organize this element. Okay. And we call it overhead. Okay. We call this overhead. Oops. Okay. So let's take number of elements n. Okay. And then in a list. So this is we are talking about a linked list. So n elements. So pointer size is p. Okay. Pointer size is p, and there's usually it's 8 bytes. The pointer size. Size of that element is e. It could be anything depending on the object you're going to store. Maximum size of the array list, the array is d, that is d, then basically storage for the array is de, right? So the array size is d and the element size is e, so storage for the array is going to be de. Okay, and for the linked list it's going to be n times because we have n items in number of elements, and for each element there's a pointer and there's the remember if you take that constructor, right, we have a next pointer and then the element inside, so p plus e, this is storage, so we have n of them, so this is the storage required. Okay, so then if we take the small of these for that particular number of data, n is actually the most space efficient version. Okay, so basically so for example, if we take an example, so again the array storage required by array is de, and for the linked list it's n times p plus e. Okay, so then the most the array list is most efficient when n greater than this, right? For example, let me annotate over here. So okay, So basically, so if array list is most efficient, basically DE less than n times PE, right? P plus E. Okay, so that means basically, so this is this, if array list is efficient, right? So that means n greater than n is over here, we're going to take P plus E into the down for DE divided by P plus E. Okay, all right. So this is the case when the array is going to be efficient. Okay, so we call this mouse. Okay, so so um, if you have relatively few elements in the list, then linked lists are more efficient. Okay, so when n is really small, okay, so linked lists are more efficient. Okay, because there's no wasted empty space, right? If the list is close to full, then array lists are more efficient. Okay, so then basically there's less wasted empty space in the array list. Okay, so how do we calculate the break-even point? Basically, we call it break-even point when at the moment when this n goes above that value. That's the break-even point, right? So for example, for p equals e, the pointer size and the data size both equal. When they both equal, p and e, so this two p's over here, and then they cancel, so then this become n by 2, right? So the array list is more efficient when at least half full. So when p equals e, array lists are more efficient when the array list is at least half full. Okay, so when n goes basically yeah, right. So so when n goes beyond this d by 2, which is the maximum size, d is the maximum size of array list. So when the length of the number of data items goes above d by 2, which is the break-even point, basically right here, array lists are going to be more efficient. Okay, so otherwise the linked lists are more efficient. Okay, so so for example, if we do this calculation, we can do this calculation, the break-even points, right? So n, so we annotate. All right, simply we need to plug this value to this formula, right? So n greater than dE over P plus E. So n, we are looking for n. Okay, so D 1000 times E is 92 divided by 92 plus 8. So this is 100. Okay, so this goes cancels off like this, so we end up 9200. So the n has to be less than 920. Okay, so that's the answer for this question. Okay, so the break-even point is, we say, 920, the number of data items. Okay, so for that means basically for an array list with 1000 objects maximum, is going to be only efficient when total number of elements inside gonna go above 920 compared to the respective linked list. Okay, the simple reason is this guy is larger, right? So that's why. So this guy is larger. Okay, All right, so okay, so let's go down. Let me clear all this. Oops. All right. Okay. All right. So space comparison. Let me see. Let me check. Yeah, space comparison. Linked list. Right. Unlimited storage up to free store value. Okay. Size is fixed. Okay. Minimum overhead only needs space for objects inside for the linked list. Okay. So when there's few elements, the overhead is high. Okay. So this is not talking about the element implementation, guys. Okay. So we are talking about broader list. Okay. So again, the overhead minimum because only needs space for objects inside. We know that objects has a pointer inside, right? So when there's few elements for the array list, when there's few elements, the overhead is high because there's a lot more empty space in there. Okay. So element overhead is more here with linked list. Require extra pointer for each node. So that's an overhead, right? So if the two data item and the pointer size is comparable, then that's going to be a like relative wastage is more when they are let's say close, right? When the pointer size and also the data size is close, the relative wastage is for the pointer is higher. Okay, and there's no overhead per element in an array. Okay. All right. I'm going to quickly go over stacks. Okay. All right. Stack basically it's a linear structure. It's a restricted linear structure that only allow insert and remove from one end called the top. Okay. So that end is called the top. Okay. So it's a top and it's a restricted linear structure that basically allow insert and remove only from top. So basically what we do is actually we actually um, um, take an array or list and sort of like we safeguard it from all like we prohibit access from the middle, we prohibit access from the bottom, we only keep it open for the from the top. So only insert and removal allowed from the top. Okay, so that's sort of restriction. You can think of it as only like a cup, so or a cylinder, one with one open end. Okay, so okay, so those restrictions make it less flexible than list, but still it's really they make it efficient, and then there are a lot of applications of those. Okay, there are many useful application of those uh, uh, efficient structure. Okay, so so since this both insert, we call it the technical term is push for stacks, and removal, we call it pop, happen at one place which is we call top. Okay, So then it's the last entered item is the one sitting at the top. So if we want to take it out, then that is going to be the first item out, right? So we call it LIFO, last in first out data structures stack. Okay. All right. So let me clear these drawings, and then we have an animation over here. All right. So we are going over push operation. Okay. So item 1 pushed. Item 2 pushed, item 3 pushed, item 4 pushed. Now we're gonna pop out them. Okay, item 4 popped out, 3, 2, 1. So now its stack is empty. Okay. All right. So let's go over stack ADT real quick. Okay. So push operation, add an element to the top. Okay. Clear, basically like in the list we basically reinitialize the stack to empty. Okay. Length operation return the length of the stack. Pop operation remove and return the element at the top. Okay. Top value, simply without doing, you access the top value basically. Okay. Access from top. Okay. So basically it makes sense to allow access to the top because it's the only place that allow access. So then without removing, you can simply take, okay, what do we have at the top? Okay, without popping it out. Okay, so that's a good operation to have. Okay, so this is the list ADT we have in our code base. So we have the stack, that's the ADT, and then again we do have those private for assignment and the copy constructor. Okay, so those are private, and the default constructor is this empty stack. Okay, and then in clear operation, and we have the virtual destructor, which is really important, and then push pop top value returns the top elements. Okay, and the length. Okay. Yeah. Okay. So before we go into analyze stack operations in detail, we're going to go over these pseudocode conventions. Okay, real quick. All right. So indentation equals a block. So we use indentation to represent a block of code. Okay. General keyword has their English meaning. Okay. For example, we use while for while loop, for loop. Okay. Same with if else and not, for conditional, and return for returning. So those keywords has the same meaning. Double slash equal indicates comment, and then this whole the convention adapted from this book actually. Okay, so it's actually really good for writing pseudocode. Okay, so going forward is basically assignment. We use the array pointing to left. Okay, so basically right, for example, right here ij basically assign both I and j to e. So that's what this means. Okay, so we assign e to both I and j. Okay, so we use the array pointing towards left, simply because assignment operation in programming works from left to right. Right to left. Okay, all right, that's why. So no global variable without explicit indication. So okay, if there is a global variable, we have to explicitly indicate that. Okay, ai like this indicates the ith element of the array A. Okay, compound data organized into objects. Then we use dot notation. to represent the access into the attributes of the those objects. Okay. All right. So let's then take a look at we have been further. Okay. Null refers to a pointer referring to no object. Okay. These are the same thing that we have in programming as well. Parameter p passed by value to a function always. Okay. That pass thing, that p can be a pointer though, but always it's passed by value but can be a pointer. Okay. So object are passed as to function as a pointer to that object. Okay. All right. So the pointer to that data in the object is copied, not the data. So object pass as a pointer. Okay. All right. So let's go over the pseudocode of linked list implementation of stack. So the function is create stack. Okay. Okay. So we have the basically create stack and then else stack. Okay. So the top is null, size is 0. So that's all. It's order 1 operation. Okay. So you can see that I'm going to use the stack like illustration to fill this up, and it's kind of a cool way to represent stack way of doing the things into this as well. Okay. So we did that. So we pushed this one first. So it's create stack. We are done with it. So it's the push operation. So we take the new value we are pushing. So we assign that to top, and we increment the size. So that's also big O of 1 operation. Okay. So we did push. So length, simply return the size. Again, it's the order 1 operation. Clear. All right. So while top is not null, basically we have to loop over and delete each element. Okay. So this is order n operation, right? So we have to go inside and delete all of those elements, and then reassign the next top value top next to next top, so that we go down all the way down to the bottom. At the end we have to assign the size to 0. Okay. So that is clear is order n basically operation. I think it's not showing here. Let me just quickly show you to go here. Kind of it's, let me quickly adjust this order in. Okay, sorry about that. So kind of covering that. Okay, order n operation. So we have clear, and then pop operation. So we have to make an assertion that whether the stack is empty. If it is empty, then we return nothing. Otherwise, we have to return the top next. We have returned that. So we first assign that to a variable, temporary variable, and we have to delete the top. Because we are popping, and then we have to reassign the top to the temporary temp value, and then we have to remove the size decrease the size by 1, and we return this value. Okay, see that top next is the temporary, and then that we assign the new top to that. So we went 1 down, right? And then we return the first top element. So we return the data value. Okay, that's it. Okay. All right. So top value we simply access. Again, there's an assertion, and then if not, we return the top element. So it's simple access. Okay. All right. So here's the an example. Okay. So first we create a stack, and then push values of this I values. Okay, and then we pop them. So this is pseudocode. Okay, so we start off with empty and we are creating. So we push pi right here. First value is pi, and then next value is 10, 15, 20, 25, and then and then we're gonna pop them. Okay, pop out 25, 20, 15, 10, and then and then it's empty. Okay. All right. So this is the actual code. All right. So we create a stack. That's the initialization of the stack. Okay. Creation, and then we push, and then we pop. Okay. All right. So application of stacks. Okay. We can represent a deck of card using a stack. Array reversal. All right. So this will be this will be going into your exam, I believe. Okay. Activation record, that is basically call stack in operating system, is implemented using a stack. If the function call goes into a stack space, basically we call it stack phase, right? And undo and redo operation in browsers are implemented using a stack. That's basically any undo and redo operation in any application. Forward and backward operation in browser also the same thing. Okay. Non-recursive backtracking. Okay. So basically, if you want to access most recent data in a series of data, then you can use stack actually. Expression evaluation in math, we can use it for a stack. Okay. An iterative depth first search algorithm in graph, that also implemented using stack. And later on in the I will actually try to add one of these few of these example as implementations. Okay, so let's move on.